Thanks for joining this hardy band of Valhalla enthusiasts here. So my name is Kai Horstmann. I'll be your speaker today. I just skip past this thing here. You probably know that the OpenJDK is organized around these projects. There's Project Amber that gives us such things as programmer productivity, or sometimes maybe less productivity if you think about the switch. Record, pattern matching. Then there's Loom, that gives us virtual threads. Panama, foreign functions, that's all great stuff. Leiden, improve startup time. And of course, Valhalla, that gives us value types. So that's where we are. So ever since Java 1.0, as you know, we've had 8 primitive types in addition to the normal reference types. And they couldn't be more different from each other, right? So the primitive types are flat. If you have an int or a double, it's just right there. There is no pointer. There's no objects. There's no header. And so that makes them, of course, more memory efficient. Equal equal compares them by value, whereas for reference types, equal equals compares the reference. Primitives can't be null. You'll see these exclamation marks will reappear in later slides, as we know. Longer primitives can tear. At least that used to be the case early on. When you have a 32-bit VM and you have a 64-bit, like a double or a long, then it could be assigned in 2 chunks, and it could theoretically happen that the current thread is interrupted when it has assigned half of a double or half a long, and it hasn't yet done the other. We'll come back to that too. And with objects, that can never happen. And of course, they're zero initialized. So those are some real differences between just regular primitive values and objects. All right, so why would we care? Well, sometimes we would like to have classes that are more like primitives. For example, if you think of things like a currency value or a measure or data time, think of a data time, you don't really care where it's located. You don't really care that it's inside some object. It's immutable. And it would be convenient to just think of it as being just like a primitive. You could compare it with equal equals, for example. Some people want different kinds of floats. Like we have already 2, right? Some people want shorter and even longer ones. There are all sorts of people. And so the mantra of Valhalla is that we want to do things that code like a class, but they act like an int. So we want to have the flatness, the valueness, but we also want to have methods, of course. And mostly the reason is, of course, performance. That if you don't have to have an indirection, then you save memory. If you don't have an indirection, you save on locality. So imagine you have a large number of values in an array, and if it's just by itself in one array, then it could fit in a small number of cache lines, where if it's distributed in objects, it could be anywhere. Also, if you have values, they're not on the heap. And so that means there's no pressure on the garbage collector to collect them. So those are the efficiency reasons. Then there's another programming reason that is because right now you have ints and integer, and you have Boolean, lowercase and Boolean uppercase, and it's a pain with these wrapper types, for example. So there's now 4 different ways of having a thing that is true or false for integers, right? It could be an int predicate, that's what you're supposed to use, but actually in a function, integer Boolean would be more logical, and there's the 2 other things in between. They're all different, and that's a stupid pain. So that's what we're going to be getting in Valhalla, and the fundamental concept is what's called a value class. So a value class gives up something. And the promise is that for giving up something, it's going to get some rewards of some nature in return. And what does it give up? It gives up the notion of identity. So when you have values in a value class, you cannot tell that, say, this value and that value, that they're different, that they have their own identity. They're just values. So that means if you compare them with equal equals, it'll always look at the contents and never at the location. Now you would say bring it on for something like dates, right? That you never cared where they were in the first place. It also means that you can't synchronize on them, because to synchronize on something, it has to be a specific thing. And you probably say, so what? When is the last time you needed to synchronize on a local date? I mean, you never do, right? Some people sometimes grab an object to synchronize on something because it saves them a few keystrokes over getting a re-entrant lock or whatever. But most people couldn't care less. Now, the promise is, of course, that when you tell the VM that this is a value class, that it may then optimize the layout or performance in some way. And that's what we're going to be looking at today. So, in fact, when Valhalla first was buildable a few years ago, I remember I was at JCrete and we looked at it and we built it and we could not tell at all whether it did anything useful. And so ever since, I've learned a little bit more about how you can actually poke behind it. And you're going to see today that, yes, we can actually get it to do something where you say that is obviously useful and it's worth the trouble. So the syntax is dead simple. There's a new keyword value that will soon be available. And you will declare a class as a value class by saying value class. And then that means that class has given up identity. And the VM can now have at it and do its value optimizations. Value classes have to be immutable, because if you could poke inside a value and flip some bits, then that wouldn't really work, right? Just imagine that like double was mutable, and you could take like pi and change a bit, and then all the other pi's would change. You wouldn't want that. So obviously a value is immutable, and so you'd say, well, probably, wouldn't most value classes be records? Because a record is already something that is immutable. And that may well be the case. We do have the option. We can have a value class, or we can have a value record. So the concept's a little bit orthogonal. And so here, today, we're going to be working with this value record point here for a long time. So look at it. The point has an x and a y. And so it is obviously something, if I have a point in 2D, that it's immutable. And if I have the origin, I don't care if that other origin that I have, where it is in memory or not. I want the VM to somehow do the best thing with it that's possible. So there's a JEP out, JEP 401, that's been out for a while. And I don't work for Oracle. I have nothing to do with them. I know for a fact it's not going to be in JDK 25, because 25 just got final. I have heard that it may appear somewhere between 26 and 28 as a preview feature, or not. But let's hope. So just a couple of pictures here to lay the ground on terminology. So what you see here on the left are values. We have the primitives and references up here that you already like, and they can be like on the stack. So the stuff here on the left is the stack, and they can also be inside objects, as you know. And now we have a new kind of values that can also live on the stack that could be, fatter, that has more stuff in them. And of course, we have traditional objects. You see an object on the right-hand side. It has a header. And then right now, that object has two doubles in it. But it could also have a single thing like that. Could also be sitting inside there. So a value is something that lives on the stack. That maybe also is a field or an array element. And an object is strictly the old-fashioned thing. It's big, it has a header, it has a reference to it. Yeah. And as an aside, sorry about this handwritten diagram. So I figured I asked AI to clean it up for me. And this is what it gave me. So if one of you actually, this sounds like something that AI should reliably be able to do, right? I say, turn this thing into an SVG. Clean it up. And it didn't work. I would love to have an AI program that can do that. All right. So now we want to try this out. And it's easy enough to, to do. Right now, you could, of course, go to this site and download it. But that thing is poorly maintained, and it generally is quite old. If you just want to play around with something really simple, you could go to this otherwise delightful site, the Java Almanac, where you can actually explore every single version of the JDK since whenever online, and it has like a little playground for them. And it's just with Valhalla, there's not that much to play around with. So realistically, if you want to hack with it, you need to build it. But it's easy enough to build. So I know how to build it on Linux with my eyes closed because I've done it so often. You clone it, you run bash configure. It may tell you that you're missing this or that package. You install the packages, and then you build it, and you're done. What you then want to do is, if you use SDKman, which I encourage you to do, if you mess with multiple JDKs, then you tell SDKman that, of course, SDKman could install Valhalla for you, except it also gives you this very outdated version, but you can point it to the local version that you've just installed, and then you can just use it to switch. And so we may see that a little later. And then when you run it, it's easy enough to do. You can use that value syntax. We'll see an example in a minute. And now we want to try something out and see if it does any good. So I figure I have points, right? A point is two doubles, and what can you do with points? And I said, well, the easy thing to do with points is you do Brownian motion. So Brownian motion means that you have like some particles that are in the liquid, and they get randomly permuted. They move around, and it's I remember from my misspent youth that in physics that eventually the particles will actually move even though they get equally bombarded from all directions. And that's just as an aside. So here's a program that would do that. So we have a lot of iterations, and we move this. Now notice here that the move by method, that it returns a new point because it's immutable. So this thing will generate a new object, as many iterations as I do. So if Valhalla does something good, then one would hope that those new objects are not actually generated on the heap, but they're just local objects in registers. Right? That would be kind of an indication that something interesting is going on. So the key thing here is that each time move by is called, it makes a new object. And so we'll see if we can, if that actually happens. Just as a first try, I'll just run this here. It makes 100 million iterations, and it is done after 7.86 seconds. Without Valhalla, it is 8.17 seconds. So that's not so far too exciting. And so let's dig into why that is the case. I'm not going to do it here in real time. You can just compile the source that I give you, and you'll get some similar relationships. So let's see what's the impact of allocation here. So if before Valhalla, what's this code going to have to do? It's going to have to 100 million times allocate a new point. So that a point has a 12-byte header on my VM here. It has two doubles, so that's and it has to be aligned on 4-byte padding. So that gives us a total of 32 bytes for each point object. So I have 100 million of them. So I would surely, without Valhalla, I would imagine that those will all be allocated. Now you could say that even in the code that you saw, that even without Valhalla, theoretically, the JIT could see that this is all local and it doesn't actually have to do the allocation. But we'll see in just a minute that it does do the allocation. So if it does, in fact, allocate 100 million points, that's about 3 gig. And we should see that. Now, how do we see that? We'll just run the whole thing with flight recording in action. And then we will look at it with Java Mission Control. So let me run this. So I'm not going to do the recording here. Also, I'm running everything with Valhalla, and you see scary messages because it is fairly strict. So let's see, we already have, so here's no Valhalla. Let's look at the memory. And so what do we see? We see up here 3 gig of memory has been consumed by point objects, and you can see here the garbage collector chugging along and ever so often collecting some garbage. So that was without Valhalla. So let's see it with Valhalla. Well, that's better. Right? You see nothing going on in the garbage collector, and you see that, in fact, those points were never allocated. All right, so that's kind of nice. So we did this, and so we're definitely happy, but we still kind of wonder, you know, why isn't it faster? You would think, I mean, this program does like nothing, right? It randomly kicks this point, and so you would imagine that most of the work is kind of in like maybe the garbage or something. But what else does it do? It doesn't. The next step then, what we do is we want to see, well, what actually is produced in code, and so you want to then run JIT watch. What you do is you have you instrument the JIT so that it emits messages as it translates the code. And so I'm giving you on the slides here all of the nasty flags that you have to do so you can try it yourself. And then you produce a log, and then you look at the log with JIT watch. So that's another interesting tool that you have. So let's just try that. So this is done with JavaFX actually, interestingly enough. So let's look at null Valhalla. So I'm loading the log that was generated. I need to start it, and then it shows me. Yeah, I just have this in the main method. Oh, that's actually interesting. Okay. So we see on the very left the source. In the middle we see the bytecodes, and on the right we see the assembly. And one can see here the assembly at that was generated by C1 and C2. So before going any further, just a quick refresher on what all that is. So you know that Java C generates bytecodes, and you've probably looked at them with Java P once in a while to see what's in them. And you know that when that the Java program interprets the bytecodes, and that was certainly true in Java 1.0, right? That's all that that Java did is it ran the bytecodes on a virtual machine, simulating some stack-based machine. But of course, what it really does is it pretty quickly decides to translate many of those bytecodes into machine code. So whenever something is called more than a couple of times, then it's going to get compiled into machine code, and from then on it's going to execute in native code. And so there's two versions of the compiler. The so-called C1 compiler does simple optimizations, and so its job is to speed up startup time, but it's not trying to squeeze out the last bit of optimization. And then there's C2, which compiles more aggressively, and it's more useful for longer running programs. So what we see here is that there's a C1 compilation, and the one that's of interest for us here is the last level of the C2 compilation. Let's see where it says level. Oh. What happened here? Oh. And so there's some definition of hotness that defines when the compiler kicks in. Now, in our case, of course, we run into this loop 100 million times, so for sure we're going to have that compiled. So typically, methods can be inlined. So that means that the code that was in the method is just stuffed in. Loops could be unrolled. We'll see an example of that later. So in our case, let's see what happens here. So we're here in null Valhalla. And so we have here a call to the move by method, and you can see here, yes, it's inlined. And when you click on it and you look at the assembly codes, you could follow along and see that somewhere here there's some move instructions that move things into some register and not into the innards of some object. There's no new objects that's being created. So we see that. We see also when we do the same thing with with Valhalla, and I'm not going to do it here in the interest of saving time. You can see that the same thing happens, that that move by is inlined. And so it's inlined both times, so you would expect that the same kind of work then happens, and that is in fact true. What you can also see, though, is that math.random is inlined, and so when you look through the code here, that's around here, you can see how that math.random is actually a fairly complex method. I'm not going to trace into it right now because they've put it here and it would take me too long to find it. But you can trace through that where math.random is, and so whatever math.random does, and it's like 30, 40 instructions, they all got dumped in there. And so that is the problem with this particular not very good benchmark, that it's just swamped by what math.random does. It does so much more work than any savings, and so that's why we're not seeing much of a speed up. And so, of course, that's a really bad benchmark, and one shouldn't be doing this. You should be using JMH and do a proper micro benchmark. JMH will then do the warm-up and all of that, and you know how to do that. So here's some JMH instructions for if you want to do that. So with that, and we'll see a bit of benchmark code in a minute. Well, actually, let's look at it right now. So where's our benchmark here? Source main Java. So I'm here doing the same kind of, oh, wait, this one's what I did first. This is the same kind of thing here. And now you see, I don't want to do the random stuff, so I just do a simple transformation here that's not random. I don't really care. I just want to do something. So I want to do a little bit of transformation because what I'm nervous about is if I don't do anything, that that hotspot's going to have one look at it and says, oh, this code does nothing, and then just optimize out everything. So I was trying to do something that was just a little bit confusing, and so you'll see the code here. So I just did this little transform, and you see that I'm flipping the x and the y, and then I'm doing some adding and some subtracting, so that I figure that's confusing enough that hotspot is not going to do anything with it. So that's what I did. And so I did this 10 million times, and now look at this. So without Valhalla, I had here whatever, 70 seconds. No, sorry, 70 milliseconds. 70 milliseconds, yes, per operation. And with Valhalla, nothing. Well, that is optimization, right? But it sounds too good to be true. And so it does turn out that when we look at the loop, you can see that it unrolls the loop. And somehow, and I didn't realize that, as it happens, this particular transform has the property that applying it 4 times does nothing. And, and somehow, the JIT notices that. And it really says, okay, it just completely takes it out. So, and so, yeah, watch the JIT, and you'll really see that the loop nowhere appears anymore. And so, and I should also say that it does take a fair amount of. I'm not super good yet at watching the JIT output, and so I keep pushing myself to get better at it all the time, because the instruction set is nowadays so complicated that one really has to stare at it and look at the instruction set table. And also the way that it's presented is not very friendly because there's traps and stuff in the code. And so it's an ongoing project for me to get better at JIT watching. But it is useful, obviously, to be able to do that, because otherwise you could not explain some of these phenomena. So if I use the random number, the obvious answer then is to not put them into the loop that you measure, but to pre-compute them. And so this is done here. So I have some pre-computation step, and then then once that pre-computation is done, then I actually run the benchmark. So then that way that works fine. So here you can make that like a state object here. That's how it works in JMH. But the key is pre-compute the random numbers so they don't affect in it. And then when you do the benchmark, now you get a very solid and respectable result. It tells you that the speed up is now about twofold. And so that's nice. And that's probably as good as you can get, right? Because otherwise there's nothing going on. So this shows the saving from the garbage collector, essentially. And from locality or whatever. But that gives you a solid saving, and it also gives you some respect of that that's not totally trivial to do these benchmarks. Yeah, and lower memory footprint, right? What's not to like? Moving on. So we now see that it is somewhat desirable to be able to do this kind of flattening. So what we want is no objects that are allocated. We want them nice and flat. And there's an obvious impediment right away, and that is that when you have like a point, even if it's a value, it still has object semantics. It can be null. So these values are not the same thing as flat. Value is simply an annotation for a class that tells the VM, work harder on this one. It is not a directive to the VM that says make this flat. So the whole way that Java thinks about this is objects are still objects, and all we will do is we will give the VM some hints that might encourage it to do something about flattening, but we will never force it into it. The VM can make whatever decisions it wants. And so the semantics is not changed, and we can still have null. Now that's going to be an issue for the VM, right? That so oftentimes the fact that something is not null can be observed locally, and the VM will do that today. So if it finds that something is never null, then it could be more motivated to move it into registers. But how does it know, like, if something is a field in an object or an element in an array? There's like no way to locally observe whether that thing is null or not. And so then that would mean that it would somewhere need some extra bit to indicate, is it null or isn't it null? So if I have like here an array of points, then there would have to be that extra bit somewhere. And as you can see, that really makes the layout much messier. Right? So if I have an array of whatever, 1,000,000 points, then I would need 1,000,000 points, and somewhere also 1,000,000 bits. They don't have to be right there, but they have to be somewhere to indicate which of those is null or not. And that is, in fact, what it could do. Or it could also say, well, I'm just not going to flatten it. I'm just going to use traditional old objects with headers. And that's what the implementation, in fact, does today. So today's implementation will never try to find some magic bit somewhere. It'll always make the decision to either flatten, and we'll tweak with that in the next 20 minutes or so, or to go to the traditional layout with references. In the future, it might change its tune and say, well, sometimes it might be worthwhile to put in the absence of any other knowledge to put in some of these nullness bits. And you could think of examples like if you had like an int on a 64-bit platform, it probably has plenty of time, space for that. But with two doubles, it's kind of tight, right? You have already 128 bits for the two doubles, and where is it going to put that 129th bit? You could think of strategies, and it could be that over time more of that will be done. So the other way out that we will be getting eventually is that we can tell the VM these particular values will not be null. And so it goes the opposite of Kotlin. In Kotlin, you have to put a question mark if something might be null. In Java, we're going to be putting a bang when something definitely is not null. So I didn't know this thing is called a bang. I thought it was called a wow, but it's a bang. So point bang means this point will not be null. And so then here, now that of course means you have to assign it some actual point. And the bang, the disclaimer is the syntax could change. I don't think that syntax is going to change. But yeah, it could. So the compiler will, of course, now check that if you assign a null to it, it's a compile time error. That's an easy task for the compiler to do. You also have to do a runtime check because it's easy enough to take steps that compile and that will fail at runtime. So here I have an array of point bangs. It's still going to be possible because of just general subtyping rules to assign that into an array of objects. And in this case, now you could put in a null, and that has to be checked at runtime, and you get a runtime exception. But of course, that's something that we've had since Java 1.0, right? Because the cast to an object array was always possible, and at this point, you could put in a new watermelon, and then you would get an array store exception. And so now, in addition to an array store exception, you can get a null pointer exception. So that's kind of, I think, a plausible change to this. And so this will actually, at some point, these non-null indications, the bangs, will come to all types because they're obviously useful. There's a few questions about how this is actually going to work out, because when you start doing this, you will find that you will want to put bangs in a lot of places because it makes semantic sense. And we already have these nullness in, like what was it, JSpecify, where you can now do these things. So and so you end up putting them in a lot of spots, and there's the question: can you somehow make them kind of the semi-default or something? And they're still exploring that part of the solution space. I'm not really going to get into it with that. It also does not play all that kindly with overloading resolution rules. As you can imagine, can you now have a method that has two versions, one for a point and one for a point bang? So there's a lot of complexity in there that we're not going to get into today because all we care today is about performance. So, but as you can imagine, that if I tell the virtual machine that something is never going to be null, if I say, here, have at it, an array of 1,000,000 points, none of them are null, then it becomes so much easier for the VM to say, oh, I can just put them 2,000,000 floats, or doubles in this case, next to each other without having to do any indirection. And that is the holy grail for us that we want to achieve. And so having having the bang will get us there. So there's unfortunately another issue, and that's this issue with tearing. So I talked about that it is allowed that 64-bit primitives may tear. I don't think anyone has seen that any time recently, because how many of you still have a 32-bit VM? And on a 64-bit VM, the assignment is atomic. And so it's not something that one observes in the wild right now. But of course, if you have a value type that's made out of a bunch of things, it could be 128 bits like we had for the two doubles, or it could be getting quite a bit longer, right? There's no limit really to the length. And so at some point, it would seem that if you just make an assignment is, after all, it copies one value, it copies each component. That's what equals does with values. And so at some point, it could become increasingly likely that somewhere halfway between the assignment that you have a context switch, the current thread loses control, and then you might have a problem. So at that point, you would have an object that is in a very unhappy state, right? So if the object has any invariance at all, then you would now be able to see one that violates one of those. So, just here as a little picture of that it's possible. You first assign the X, then you lose context, then you have another assignment into the same target. That other one succeeds completely, then finally we gain control over here, and now we have the x from the object over there and the y from this object. What we will do in the sample program is we will only generate points where the x and y coordinates are identical. We will shuffle them up in multiple threads, and we will in fact observe that sometimes we end up with points where the two coordinates are not identical, to show that this will happen with Valhalla, with today's Valhalla build, without. I mean, it's easy. It's very easy to generate these cases. And now, the way that it works today is that the programmer of point has to say, "That's fine with me." That the implementer of point, have decided that it's okay to have this this risk, and the syntax may change, but the current thinking is that one has to implement a marker interface. You know, is that smart? I don't know, but that's today's thinking. I mean, generally one is nervous about marker interfaces because they're inherited, but a record is final. You can't extend a record, so there it's not so bad. So that may well be the syntax that we end up. And so, well, is that now madness from the point of, I mean, why would the programmer of point ever do that? Well, I mean, the programmer of double for 20-some years has done nothing else, right? Every time that you used a double, you theoretically had the possibility of it tearing, or a long. And it hasn't stopped the world from using doubles and longs, because obviously it's a performance issue. If you want flat arrays, then that may be the price to pay. And so that is something that if one has these kind of heftier value types, that one will just have to think about. Could one switch to a different model where at use time, you could say, for these particular points, I'm okay with tearing? That's harder to do, because then you have yet another marker, right? Then you would have, like, whatever, a splat for, like a star for tearing or something. Then you have exclamation marks and another marker. So they didn't want to go that direction, because it's it just makes it more complicated. But it really is an issue, because if you you don't want it to make the default. You don't want to be insecure by default. That was bad enough with double and long, and so you have to have some way of allowing it, and that means either the class designer makes the decision or the class user makes the decision. So that's where it's at. What if you have one of these unsafety things? Well, we know how to do it, right? Then if you do assignments, then you have to either make sure that this only happens in a single thread. I mean, if within one thread you move from here to there, it's not a problem. It's just that if you move into the same target from two different threads. But if the target is confined to a single thread, who cares? Or if the target is shared amongst multiple threads, you can do what you always did when you shared something about multiple threads, and use either volatile or locks to control that. It's just something you have to do. So, and I said you can observe this, so let me show you how to actually observe that. This is what's called a phase 2 feature. So the current Valhalla build supports the syntax of what's called phase 1. And phase 1 is nothing but the value modifier. Anything else, there's no syntax for it. There's no parser for it yet. So the bang syntax is not there in the current build. You can't put a bang. It's just a syntax error. And because they first want to play with the semantics before they finalize the syntax. So anything that uses anything other than value, you need to use the some annotation. So there's an annotation called null restricted, one that's called loosely consistent values to allow tearing, and there's a couple others that we will see later. So what you have to do then is you have to allow those internal annotations. So you have to do the usual kind of module defeating thing that we all love to get the thing to compile. And so let me just show you the program that we're doing here. to show the tearing. So we're having a few threads, and they're all gang up on moving something into a shared point, that's this thing R, and then we're going to be observing it, and I have to, for a technical reason, I also have to put it in a box, because if I don't put it in a box, then Valhalla won't do anything with it. I don't know why, but Remy told me that I have to do that. So we're boxing the point just today to keep Valhalla happy. We're generating all the points, where are they, so that they have the x and y coordinate the same. And when we see that the target that's shared amongst multiple threads violates that, then we say aha. And so when you run that, then sure enough, you're going to get a bunch of messages. I mean, not like super many, but it was a screen full of messages that said, now it happened that one of these things has been corrupted. And so this corruption really does happen. And if you do it without this annotation, if you take this loosely consistent value thing off that I have up here, then it's guaranteed not to happen. But you also don't get the benefit of Valhalla. What it simply is, it simply will not do the flattened layout. So you could argue, well, does it have to give up flattening? It could also find some other way of protecting the whole thing, right, with some kind of a locking mechanism. Today, it does not do that. So today, it only has two strategies. One is that it uses the traditional object layout, where you just don't have the problem because it's only one reference assignment. Or if you're willing to say loosely consistent, then it will do the flattening. Yeah, and the box thing here is a temporary thing that one just has to do today to get Valhalla to kick it in. All right, so we see some of these features, and that's kind of interesting. Moving on. The last exclamation mark was that, and it's probably something one doesn't think about too much, when you have a primitive, it's of course initialized with 0 bits, right? You have an array of 1,000 doubles, and you get an array of 1,000 zeros, and that's just fine. And that's the 0 initialization is not always appropriate. Like, we want local date at some point to be a value. Now I might have an array of 1,000 local dates. Well, what value should they be? January 1st, 1970, all of them? Or like what they did in the Social Security Administration 150 years ago. I mean, there's no really safe default for dates. And so that's just the way it is. All right, so we need to have some way of dealing with the fact that explicit initialization sometimes it has to be a thing. And so that's what we're going to be getting with value types. You will have to, we'll have to what's called strictly initialize them. And so I guess I should, to get to the final point, I'm not going to get into the finer points of strict initialization. So the way it's going to be is that if you have something that is null restricted, where the null is no longer becoming a default, that the VM is going to make it so that you have to initialize it. With instance fields, you have to do that before calling super, so that the non-initialized value can never be observed, not even in a superclass. With static fields, there's some way of doing it. With array elements, there's going to have to be some special syntax. And so we don't really know what the syntax is going to be. Maybe one just gives a default value like that, or maybe you give a lambda for the defaults, or both, or whatever. Now, the final point that I want to make is, if you now do all of those things, and so if you here I want to have an array of 1,000,000 points, and I want to see that I really get a flat array of 1,000,000 points and not pointers. Then I have to make it so that point is allowed to tear, that right now we don't have the new operator that works in the way that you saw briefly on the previous slide. You have to call an internal method to achieve the same effect. I'm going to call that method, and I'm going to say the instances, the elements are null restricted, and also that the array is, that the assignment into the array is non-atomic. When I do all of that, and then I run it, and I'll just give you the instructions to run it. And then I look at it with J command. When I look at the heap, then I will see what I've always wanted to see, namely a humongous linear array of xy, 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 xy. Okay, so it does actually work. And that's where we want to be. All right. So you've now seen how you can actually observe this with today's build. It is working. Any questions? Yeah.
How often do we observe this value tiering, and what does it depend on?
You will observe it. So you will observe it when you write to the same value from two separate threads.
Yes, but like the longer your value is in memory, more often it's gonna.
Probably. But I mean, even if it happens once, it's once too many.
Well, no, actually, I'm thinking it fits non-deterministic computing very well.
Yeah, I would. It's not the most ideal way of doing something non-deterministic, so I wouldn't do that. Yeah.
So the tearing always happens if your value class has a value which exceeds 64-bit.
Yeah. And in fact, with today's implementation, if you take two shorts, it can still tear. Because they're not trying to make any effort to assign the two shorts atomically. All that they currently do is they make two assignments. Yeah.
Back to the primitive wrappers. I think that the idea is also to make them values.
Oh, absolutely. So at some point, integer is supposed to be essentially the same thing as, int is the same thing as integer bang. And double is uppercase double bang. So that is the great hope. And so at some point in the distant future, it will be so that you can declare an array list of int, angle bracket lowercase int, and you will get an array list that's backed by an int array in 10 years. Yeah.
Would this optimization also work for Boolean value types?
Will it give you one bit? The VM can decide to do whatever optimization they want to decide, but they do kind of go by use cases. And so I don't think that you're going to see that anytime soon. I mean, even today, the VM could have decided if you have a Boolean square brackets thing, that they could optimize it out, but you don't see that. People do not have Boolean arrays like that. They would then use a bit set. Yeah?
And does this also work with generics? Now you cannot use int, double, and generics?
Eventually it will work, but it's complicated. So I could give another whole talk about why that's complicated.
So the first, when it is introduced, then if you put the value keyword in front of a class or a record, it cannot be used in generics.
Oh, you can use, no, you can definitely use it in generics. The difficulty is that, so that part will come soon. The difficulties is, can you have an array list of point bang, for example? Is it convertible into an array list of not point of others? Or if you have an array list of int, is it backed by an array of ints? If you have an array list of integer bangs, which we think should be kind of like ints, is that backed by an array list of ints?
I see the issues.
Yeah, and yeah, so there's a whole can of worms in there. Yeah.
In the stream API, will it use like boxed syntax like anomaly?
See, that's the next question. Can we in the stream API get rid of int stream? And there I'm more hopeful, because in the stream, the problem with the stream API is it produces a whole bunch of intermediate junk, and it has to do it in the way that the JIT can optimize it all away. Right? It builds this big pipeline, and the pipeline is cunningly built in such a way that as soon as the JIT runs through it a few thousand times, that actually none of this stuff happens. And so that is not as, because then you don't have to make the array decision. Then it's just a wrapper with a single int, and that's easier to JIT out. Yeah?
Now you see performance gain with using value types. Isn't it possible to do similar things in the JIT compiler instead of in the language itself, with escape analysis or something?
I see. So the thing is, you can only go so far with escape analysis. So escape analysis can tell you something about locals, but there's no escape analysis that you could do that could tell you whether a whole array can be flattened out. Because how would you know? I mean, if you don't tell the JIT that this array will never hold a null, it can't really speculatively say, well, I'm first going to make it into an array of doubles, and then later when the null comes, then I'm going to reorganize the whole array and rewrite all the code that accesses to it. That's too risky an optimization to do. I mean, that's too hard to de-optimize. And so the whole game is we want to empower the JIT with just the minimum amount of information, of extra information. That's where value and bang and the tearing thing come in. Those are the three knobs that you have to nudge the JIT into the proper direction.
Tearing with the
Yep.
with the consistency, that would only apply in case there is threading going on.
Yes, absolutely, absolutely. So yeah, if you don't care, if you never worry about multi-threading, then you don't personally have to think about it. It's just a bit of a burden for the class designer who does not know in what context that class is going to be used. Okay, I think that was it for questions. So just come up to me if you have more questions. You have the URL if you want to download and play with the code yourself. Thank you.